Hello, and welcome to our talk today on using GastroPlus as an educational tool, or how to teach pharmacokinetics with University Plus. My name is Noam Morningstar-Kywi. I'm a scientist at Simulations Plus, and I'm joined here today by Ian Haworth, an associate professor at the USC School of Pharmacy.
Okay, well, thank you, Noam, and thank you also to the organizer of the meeting for giving us the opportunity to talk about this subject. And what we're going to tell you today is a little bit about our efforts to teach GastroPlus, and both in terms of the software operation and teaching the underlying scientific principles. And so we'll go to the next slide. And so I don't think I need to tell this audience that PBPK modeling is important and that it's increasingly used both in industry and academia. But I think particularly those of you in industry will be interested to know that there really is extraordinary interest in this area among students, and they see this as a growth area. They see it as a very important area, a very contemporary area to learn, and they want to do PBPK modeling classes. But as all of you know, to really appreciate and perform PBPK modeling effectively, you do need an in-depth understanding of biopharmaceutics and pharmacokinetics, and that's not an easy level for most students to reach. So on the one hand, the use of teaching aids, of computational teaching aids and other aids can help to understand, can help to increase understanding of pharmacokinetics and biopharmaceutics among students. And that's been shown over the years. That is a very practical approach. The challenge here, though, is to teach advanced scientific principles and software operation in parallel. And that was something when we first started considering this course that we really did think would be a challenge. I think we have achieved that. I hope that we'll convince you that we've achieved that in the next half an hour or so. And furthermore, we have produced a template that allows us to describe what we have done, and hopefully to transfer our approach to other settings, that is to other universities, that will allow faculty in other universities to implement similar courses. So if we could have the next slide. This is a broad description of the course design and how we thought about this problem of teaching science and software at the same time. So clearly, we need to teach some scientific principles. Those are pharmacokinetic principles, biopharmaceutic principles. And on the other hand, we need to teach software operation. We need to teach use of GastroPlus, of our Met Predictor, of other Simulations Plus software. And we connect those two circles with prediction. So we would like to have the students understand the scientific principles, and then use the software to make predictions and interpret those predictions based on their understanding of those principles. Having taught the use of the software, we can then start to have the students build models. We refer to this then as the simulation element, the connection between functional software operation and actually developing models for application, which is in the green circle at the bottom of the slide, where that can be at a very limited level or actually a very sophisticated level in developing models to test hypotheses. And that then takes us back to the scientific principles, because in order to evaluate those hypotheses, it's necessary for the student to understand those principles, both in developing the hypotheses and in understanding the outcomes of the model. And so all of that put together in the center develops a appreciation and the ability to perform PBPK modeling and reach conclusions on drug disposition for different patient populations, and as you'll see, different formulations and other variables that have an impact on that disposition. So this is our overall course design principle. To reduce that a little bit more to a practical concept, if we could go to the next slide, you see the same Venn diagram, but this time with an example. So the example here is relatively simple. The scientific principles involve pKa, solubility, rate of solution, and absorption. We're applying these principles here to midazolam, and then in the blue circle, we're going to use the software to generate, first of all, a pH solubility profile. You can see that profile in the top right of the slide. And that profile allows us to talk about some basic principles that include that midazolam is a base, that its solubility increases somewhere around pH 4 or 5. And that's linked to the fact that that is where midazolam ionizes. So midazolam is a weak base. pKa, the predicted pKa is 4.57. We asked the students to look up the experimental pKa to try to understand why midazolam is a weak base. So this is generating understanding of the principle, and also in order to generate that pH rate profile, the pH solubility profile, I'm sorry, we have them actually use the software. Then in the bottom figure, we have a curve generated in GastroPlus for the dissolution rate on midazolam. You can see the red curve indicates essentially instant dissolution in the stomach, but then as the pH increases, as the drug moves down the gastrointestinal tract, there is some precipitation. So this allows us to think about the pH in vivo and how a weakly basic drug would be likely to behave as the pH increases in the small intestine. And then the light blue curve is showing the absorption of midazolam and showing that absorption is complete and relatively rapid, and that then can be brought back to the log P of midazolam, the hydrophobicity, and the likelihood that there'll be good passive diffusion. So that really takes care of the scientific principles and the software operation and the prediction. The simulation in this case is not really model building, but more just the ability to generate those relatively simple pH solubility and dissolution and absorption curves, and then do that for other drugs. And interpret the same curves for different drugs in terms of their physicochemical properties. So I hope that gives you a sense of the course design. And now we'll take a closer look at the template. And so we go to the next slide. So the way that we look at the course, still an overview, is there are really three parts. The first part, the science, is focused on biopharmaceutics and compartmental pharmacokinetics and fundamental principles. The second part goes on to a PBPK model and includes the discussion of metabolism and transport. The software operation is performed in parallel with those discussions of the science. So, as I've already described, looking at generation of curves that reflect physicochemical properties, moving to PK plus to develop a compartmental model, and then go into a PBPK model, developing that model and refining the model and including enzyme and transporter kinetics. All of that is therefore aimed at model building. Part 3 is aimed at using the model to test hypotheses, to consider a hypothesis for a given drug and to model, to use the model to investigate that hypothesis and understand outputs from the program. And all of this is driven by a group project, typically 4 or 5 students in a group working on a single drug, and we'll get to those drugs and some examples of that later in the talk. So the other thing that we are interested in doing from an academic perspective is, of course, to assess whether the course is effective in increasing understanding of the physical, chemical, biopharmaceutic, and pharmacokinetic principles. And so we'll also show you towards the end of the talk our approach to that through a pre and post course quiz, which is very much designed to test understanding, not necessarily to test knowledge retention per se, but understanding of principles. So we'll come back to that in a few minutes. And I should say that we've offered this course once last year as a 15-week elective for master's, PhD, and PharmD students. We are implementing it again currently in a similar format. So we have very much learned, we learned many things about the appropriate implementation last year. We're testing them further this year, and I think this is giving us a good basis now to transfer the course design. So with that, I'll hand over to Noam, who will now talk in a little bit more detail about the GastroPlus implementation of the course.
Yeah, thank you, Ian. So to look at a little bit more detail of our course template, starting with part 1, there are 5 topics in this part, and each of them took 1 week in our course. You can see we start with an introduction to the principles of modeling, and that moves on to cheminformatics, making predictions with ADMET Predictor, and just starting to build a model and talking about what it means, what model building is to begin with. Then we move on to more drug disposition relevant topics like dissolution absorption, compartmental pharmacokinetics, and ultimately a midpoint presentation. And so you can see in the middle columns, there's a scientific concept and a corresponding GastroPlus activity, each of these mapped to the corresponding learning objectives or skills that we want the students to walk away from the class with on the right-hand side. And these are designed to advance in parallel, hand in hand, the interdependent science and software. To take a more in-depth example, looking at compartmental pharmacokinetics, this can be guided by the overarching question of what is the relationship between absorption, distribution, and clearance. If we start on the left-hand side, this is a plot based purely on ADMET Predictor properties from midazolam with a 1-compartment model. You know, I look at this, you look at this, we may all be pretty familiar with a CP time profile that looks like this, but it might not be as clear to these students who are just starting out in the world of pharmacokinetics. You know, they might recognize things like Cmax, Tmax, AUC, but things like an absorption phase, a distribution phase, a clearance phase might not be quite as clear to them. And so it's important to take some time to explain what these are and why they exist and what the relationship is. And that can be helped certainly using the software. Down on the bottom left, we see the inputs in GastroPlus for a compartmental model, and we can ask the students to start putting in values to change the clearance or the volume, add a second compartment, and see what effect this has on the curve, and if that makes sense based on what they're seeing. But of course, we don't want this to be purely abstract. So if we move over to the right-hand side, we see a compartmental 3-compartment model from midazolam IV fitted to observed data. So the blue squares are the observed data, the blue line is the simulated line in GastroPlus. And we can make it a little bit more tangible this way, showing students how this compartmental model does, or in some cases does not, accurately describe the observed data for the drug. And what I want to point out here, I have an IV model shown as in this example intentionally because it's a good discussion point for the students how you can, when you do fitting to IV data, it isolates distribution and clearance from absorption and is a good practice in modeling to do it that way, but also to make sure they understand the science and mathematical reasons behind that. And we did all this using the PK+ tool within GastroPlus. That's what's shown in the middle of the screen, the fitting with PK+. And we can see that this fitting worked pretty well for the IV dose and the two lower doses in green, light blue, and red respectively. But the compartmental model actually isn't working as well for the highest dose in the dark blue. And this leads nicely into the next, both in terms of this presentation and actually our class with the students, into the next section, part 2, which focuses more on the whole body PK with PBPK models and nonlinear metabolism and transport. So those are the two major topics in this next session. We spent 2 weeks on each, and that's followed finally by a session on model refinement. And again, same structure where we have the didactic science about tissue distribution and the corresponding software activity of a PBPK model. Same goes for enzyme and transporter kinetics, and again, the learning objectives to guide all these on the right. So looking at a detailed example for these, we have on the top and middle, we have midazolam on the top, and on the bottom left, we have metformin. And over on the right, we have the generic PBPK diagram, which is an integral part of GastroPlus. And this in and of itself is a good teaching tool because it's a very nice diagram connecting the different tissues in the body, showing blood flow and perfusion and how they're all connected. And this is really, just a description of how the drug is going to move throughout the body. Of course, there's a lot more detail to these tissues, which is where opening up this tissue detail panel helps as well. Looking at the midazolam example for the liver, this gives a list of all the transporters and enzymes present in the tissue. In this case, we're looking at the enzyme CYP3A4, which is the metabolic enzyme responsible for midazolam's clearance. And here we can point out to the students, right, look, CYP3A4, it's in the liver. We have an expression level here, and have them move to the enzyme table, put in the kinetics for midazolam, which they would have looked up and implemented into the table. And then most importantly, look at the outputs. So they run a simulation with this. We can see how well it does or does not describe the observed CP time profile. But we can also look at the amount metabolized in the liver, the total amount metabolized, and try to start to make connections between what is actually happening to the drug and what we're seeing. Right? In this example, we see that the bulk of the metabolism is actually occurring outside the liver or in the gut. And this is a really good description of why midazolam has a high first pass effect, and we see dose nonlinearity with that. Another type of example, looking at metformin. This molecule, on the other hand, is cleared almost exclusively renally, both by filtration and active secretion. And so if we use GastroPlus to open up the kidney tissue detail panel, we can then see our glomerular filtration rate, set up renal clearance to be fraction unbound times the filtration rate, and also go to the transporter table. And again, the students will look up this data, use the metabolism and transporter module to convert it to in vivo kinetics, and add MATE1 and OCT2 for the active secretion of metformin. And then, they can see in the program, here on the left, we're showing the outputs for the tissue concentration, showing both how in the kidney, OCT2 helps get metformin into the kidney, and then MATE1 also effluxes it into the urine on top of the filtration clearance that's occurring. And the goal here, really, in addition to having the students learn all these detailed aspects of software operation, is to demonstrate and show the mechanistic reasons behind drug disposition in the body. And so we're moving from the somewhat abstract compartmental model that might describe it but doesn't physiologically represent it, to this more mechanistic model where students can tie in their scientific learnings for each system and relate it to the drug's physicochemical properties and how the drug interacts with those tissues or systems. And then lastly, in part 3, of course, the students get to apply all this. And by apply, we mean they take this model that they've built and now they apply it to new questions. So we provide them with prompts, which I'll come to in a second, and they're going to use this model that they spent the last 10 weeks building to come up with answers to these prompts. Now, the first part of this is developing research questions. Of course, as scientists, we know how important it is to have a research question and a hypothesis we can test. However, it's also important to note that a key part of this is devising a modeling approach that actually can test that hypothesis and provide you with an answer. So tying in that question to how am I going to set this up in GastroPlus to be able to test my hypothesis. Then we spend time running simulations and making the prospective predictions, iterating through that, followed by interpreting the results, figuring out what it means. Is it significant numerically? Is that numerical difference significant clinically? And this all culminates in their final presentations, where they review their model, go through the questions that they explored, and present their conclusions. And so the prompts that we used, we tried to make it so they could be unique to each student group's drugs. So we came up with 2 prompt stems, one, the first one here on the upper left, relating to patient populations, and number 2 relating more to classical ADME parameters such as formulations or food effect. And in each case, the X in the stem can be replaced with a term from the second column that makes it relevant to that drug. So is the drug going to be important in elderly versus pediatric populations, renal impairment, or similarly, is this a drug where you want to look at food effect, maybe formulation type, manufacturing process, or particle size? And so these were specific to each group's drugs. And we have some examples of that on the right. So for metformin, they looked at, is it going to be safe and effective in a renally impaired population? What about MATE1 or OCT2 variant patients, or what about dosing schedule? Ibuprofen, similarly, they were looking at pediatric patients, CYP2C9 variant patients, and they looked at formulation and food. And I would note here, from an academic perspective, we have 3 prompts for metformin and 4 for ibuprofen because in this year that was the number of students in the respective groups. And so we found as teachers that this having multiple prompts was a helpful way to split up the work among the students and get everyone engaged. So they're all working and using the same baseline model, but then they each are responsible for exploring their own area and sharing their findings on that as well. And the core way we drove this with the students is really to try to get them to think, first, how do you set up a patient physiology to represent one of these groups? How do you take what you know about a specific population and represent it in a model? How do you try different dosing regimens? How is that set up? What results are you looking for? Both how do you find the simulation outputs that you need in GastroPlus, and how do you interpret them, and how do you define what's significant? And then most importantly, how do we assess safety and efficacy? Because it's important to remember, everything we do comes back to administering these drugs to patients and to not lose sight of that. And so we bring this back around to, is this drug going to be safe and efficacious in this patient? So to give some examples of these group projects, first I want to talk about that metformin prompt. And I'd like to note that this is the students' work. We're presenting it here, but this is all based on their project that they accomplished in the class. So this question asking if metformin is going to be safe and effective in a renally impaired patient. Right, metformin is a small, hydrophilic, mostly cationic, a physiologic pH drug. It has low protein binding, kidney transporter substrate, and like we already discussed, it's almost exclusively renally cleared. So this is very relevant to patients with renal impairment. So physiologic question, of course, how do we represent renal impairment in GastroPlus? They either have learned it in other classes or they can look it up. Renal impairment is generally characterized by reduced renal blood flow and glomerular filtration rate, both of which are parameters that can be entered in the model. And then after they do that, they can run their simulations at different doses and test this in a healthy versus a renally impaired patient. And that's what's shown in this plot. If we look first at the black squares, that's the observed data that one of the studies that they fit their model to, and the black line is their baseline model. So a healthy patient with a 500 mg twice daily dose, which is a standard dose for metformin. And we can see that their model described the observed data quite well. Then when they run the same dose in a renally impaired patient by decreasing blood flow and GFR based on values that they would have researched in the literature, we can see in the blue line that the plasma concentrations pretty quickly exceed the toxicity threshold, which again is something that the students would be responsible for researching. However, if they test a different dose, and in this case they lined up on the dose of 250 milligrams once a day, in the renally impaired patients, we see that the clearance, of course, is a lot slower, but that it stays below the toxicity threshold with this dose reduction. And so that would be their ultimate conclusion from this project, is based on the model that they built and applied, metformin would be safe and effective at a lower dose, but not at the same dose in this population. We have a similar example for ibuprofen. This one instead is a CYP2C9 substrate for clearance through the liver. And the population that they chose to look at, which relates to that, was pharmacokinetics of CYP2C9, looking at a population with decreased enzyme expression. And so, same question, how do you represent this in the model? In this case, there's actually two ways, right? They can do decreased enzyme expression, which is most likely closest to the real-world effect, or they can just reduce the activity, that is, decrease the Vmax in the enzyme table in GastroPlus. Mathematically, the equations are combined, so the net result of total activity is the same. And this kind of leads to a good discussion of software operation of how do you balance making it as realistic as possible versus what's accurate and functional. And either approach works. I don't actually remember which one they chose to use, but it doesn't really matter, is the point, as long as they were able to operate the software in a way that was successful. And similar graph to the previous slide, where they're in the black, their baseline model fits the observed data pretty well. They're using a standard dose, which was used in that study from which the observation came, of 400 milligrams of ibuprofen every 6 hours. And we see here that once you reduce CYP2C9 activity, a single dose, again, has much slower clearance, but it stays well below that toxic threshold that they found in the literature. So a single dose of ibuprofen would likely be safe and effective in these patients. However, Q6-hour dosing within 3, 4 doses starts to exceed that toxic threshold. And so this really becomes a question then of how this drug is going to be used, right? You might have a headache, take ibuprofen once and then call it a day, or you might sprain your wrist and take it around the clock for 4 or 5 days. And it's that latter scenario where this really starts to become important. And that's the type of interpretation that we're asking the students to do. And so with that, I'd like to pass it back to Ian, as we've just talked about these projects that the students have done, so we can see how they're utilizing the software. But I'll leave it to Ian to discuss their actual learnings scientifically from the course.
Yeah, okay. So thank you, Noam. And I think it will be apparent to everyone that, based on Noam's description, that the students are learning a lot about software operation in order to get to the kinds of results that we've just heard about. And so that I think is a given. But the question I think also that we need to answer is, are they developing the scientific understanding at the same time? Because that's certainly our goal here, is to teach both of those in parallel, and hope, frankly, that the scientific understanding develops. We did not really spend a lot of time in the sessions talking in a formal lecture sense about the science. We just let it happen as a process of using the software. So in order to assess that, we came up with a pre-post assessment that is very much based on examining that understanding. So just to take you through this somewhat briefly, we created a data sheet. This is for midazolam. In the top right corner, it's a combination of some physicochemical properties, a little bit of metabolic information in the table. There's a pH solubility curve in the top right. There's a couple of plasma concentration time curves that are based on different doses and different formulations, and a little bit of pharmacokinetic information. So the students were provided with that data sheet. This was for the pre-class assessment, pre-course assessment. We have a similar one for the post-course assessment for loratadine. And then we asked 12 questions, 4 in the area of physical chemical properties in red, in purple, 4 in the area of biopharmaceutics, and in green, 4 in the area of pharmacokinetics. And of course, we're happy to provide these questions to everybody as part of the course template, but they are aimed at understanding of interpretation of the data. And we did this as a low stakes test. We're not grading students based on their answers, but we are definitely interested to see the quality of their answers. We gave them 1 hour before the course and 1 hour after the course for these assessments. Questions are the same, pre and post course, the drug is different. We wanted 3 response answers, so this is not multiple choice, it's answers 1 or 2 sentences. We have a rubric, which again, of course, we will make available, that allows some grading of the questions, and each question was worth 3 points. Each section, therefore, is 12 points. The total possible score is 36 points. So how did the students do? If we go to the next slide, this is our results for, can we go to, yes, there we go. This is our result for the for last year's course, and we show the data on the left hand side for the 3 different sections, and we were happy to see that we saw strong improvements in each section. The physical chemical properties were already fairly well understood, and that probably reflects the background of the students, but we were able to improve understanding in that area. Biopharmaceutics and pharmacokinetics, a little less well understood before the course, but good improvements. So overall, then, the total scores improved from an average of 18 to an average of 25.6 from pre to post course. The other thing that we noticed, if we look at the figure on the right-hand side, is that we did have 2 fairly clearly defined groups of students initially. We had those who were scoring 20 or above in the pre-course survey, so they were already quite well informed. We saw, in general, improvement for all of those students, modest improvement, but they were already quite sophisticated in the science. We then had another group of students who were scoring 12 or less pre-course, and we saw much greater improvement for those students. So the conclusion there is that the course is applicable both to students with already a relatively sophisticated understanding of the material, and also similarly applicable to those who perhaps have less understanding. So this was a reassuring result. So we'll move to the next slide. So what do we conclude from all of this? Well, I think we certainly conclude that use of GastroPlus through the University Plus program is a really effective teaching tool that, most importantly, we can get the students to use hands-on. We can get them to use it practically in the classroom setting. And that's extremely important. I think this for the students, this is a huge opportunity to use contemporary software and to learn the operation of that software. But also, whilst they're learning the software, they are also developing their understanding of these crucial areas of science. And in fact, their learning of the software, I think, is promoting not only their understanding, but just their interest in these areas of science. So it really cuts both ways here. They're learning software and they're learning science, and as they learn the science, their appreciation of the software increases. And so this is really what we were trying to achieve, to try and teach the science and the software in parallel, and to become not yet sophisticated users, but certainly users of GastroPlus, and users of GastroPlus in a strong clinical and scientific context. And we hope that we've also convinced all the educators in the audience that this is a course that would be of interest in their universities. And we do have a well-developed template that we hope will assist all of you in teaching a similar course. And of course, we're very happy to interact with you more in trying to promote that activity. So if we go to the next slide, we now have a Q&A session, and we've given this presentation in a number of different forums previously, both formally and informally, and we do get some common questions. So we thought we'd try and answer one or two of those questions right now. So the next slide, please. So the first of these questions is, what have we learned after teaching the course? And we've certainly learned a lot. And I'll turn that one over to Noam to start that answer.
Yeah, thanks, Ian. So one of the biggest things I learned is that when we're working with the students, the order is really important. If you're like me and you work with GastroPlus all the time, it's very easy to treat it all equally. But for the students, we need a logical order so that we don't overwhelm them. And from that, and we're doing it this year in the order of compartmental PK followed by PBPK followed by metabolism and transporter. That was probably the biggest change we made compared to last year. And the reason for that is this approach allows us to do compartmental PK and fit our compartmental parameters, including clearance, to that. We can then move on to PBPK and use the non-compartmental analysis clearance from the PK plus fitting to do clearance-based PBPK modeling. Of course, not the only approach to PBPK modeling, but we found that approach works well with the students because it results in a model where you're altering one variable at a time. And then, of course, speaking of those variables, you can add metabolism and transporter back in to make it more mechanistic in the end. But what we found that's a logical order that's easy for the students to follow, and so they're able to engage more with the software rather than just getting frustrated.
Yeah, and that's been an important change, I think, that we made in the current course compared to the previous version. The other thing that I think we understand very clearly is the importance of getting the students to verbalize every week what they've done in the previous week. I think this is true in many courses, and particularly perhaps in this one, that students can perhaps listen to an instructor, they can understand what's being said, but when they have to explain it themselves, that's the real test. And so we've very deliberately included quite a lot of time each session devoted to that kind of activity, where we can hear from each group what they've done in the past week and talk about both the practical issues of operating the software and the underlying scientific principles. So that's it takes some time in each session, but it's well worthwhile. It's a big contributor to student learning. So talk about time. The second question, which I'm sure everybody who is a faculty member will be asking at this point, is how long is this going to take for me to implement this course? You know, am I going to be spending my entire semester on this course? So should I answer that question, Noam? Or
Sure,
do you want to say, okay, let me answer that. So I think it's certainly true that we spent a good amount of time developing this template prior to our first offering. We hope that effort that we put in will reduce the time required for everybody else. And that, of course, is the goal of creating a template. I think we noticed this current semester we are spending 2 hours a week in the actual teaching of the class, we're probably spending 4 more hours on looking at student reports and considering how to approach each session. But the time commitment has been moderate and certainly manageable from my perspective. And I don't really have anything to add to that. No.
I would add it's manageable. I just want to reiterate that it was certainly more time last year than this year.
Yep.
But this is true of any course. Last year we were coming up with a lot of material. This year we can use it. Again, a lot of it included some pre-recorded videos we made on software operation that have been really helpful. And so there's certainly an economy of scale. And I think the more we offer this course, the greater percent of that time we commit is to just working with the students, either in class or supporting them. And of course, at least for me, that's I'm sure I can speak for you as well, Ian, that's the most rewarding type of way to spend time.
That's right.
So I'd say it's moderate, but certainly worthwhile this year.
Yeah, that's right. I think so. So finally, I hope many of you are now asking the third question, which is how do you get more information and how can you create a similar course at your university? So we'll go to our final slide, and Noam, maybe you can talk a little bit more about the University Plus program, which really is the critical element here in providing the ability for me to offer this course at USC and for everybody to offer similar courses in their own university.
Yeah, and I'm quite grateful to Simulations Plus as well for being willing to support this, not just providing access through University Plus, but also to being supportive of the course as a whole. But with respect to University Plus, it is a program that we offer to provide access to GastroPlus and related software. So you also have access to Admit Predictor and some other resources. It's provided for free for academic use to qualifying institutions. And that's really the first key part of being able to run this course is, of course, getting the students and the faculty access. And more information can be found at the link shown there for our University Plus program or by emailing us at Simulations Plus. The second part, of course, to being able to run this course is actually getting the course designed and up and running, which, as Ian has said, we hope this template that we've presented here will help with. Contact info for Simulations Plus, and Ian is also up there. For any questions about additional materials, how to implement the template, or any other support that we can offer.
Yes, and if anybody wants to contact me directly, I'd be very happy to talk more about this from the academic perspective. Finally, this photograph that I'm sure you're all looking at the moment. This is us in action during the course. This is Noam in the bottom left corner there of the photograph. I'm on the right-hand side. At the back is a colleague of mine at USC, Dr. Rebecca Romero, who was also involved in the course last year. This is actually outside the School of Pharmacy at USC. This was in January 2022. We just about got back to campus for real after all the pandemic difficulties, but we were still being encouraged to hold classes outside. And so this is PK modeling al fresco. The students are all sitting there outside the building. One thing that really makes me happy about this photograph is that there are master's, PhD, and PharmD students pictured, and so certainly shows that this kind of course is appropriate for students in lots of different degree objectives. This photograph, I should also say, was not posed. We did not know this was actually happening. This class caused a lot of interest. We ended up getting the photo of the month at USC for this, which was a nice little bonus. So I think I will finish with that thought that this is a course that I think is applicable to lots of different student groups with lots of different degree goals, and they can all benefit from this kind of material. So with that, we'll finish. I'll once again thank the organisers for the opportunity to talk, and I hope that everybody will be stimulated to think more about how you might offer this course in your university. So thank you.
Yes. Thank you, Ian, and of course, thank you to all of you, our MIDD Plus attendees.